Hi, this is Somaiah, working as assistant professor in the Department of Mechanical Engineering. Today, as I have discussed the types of fluid flow and the fluid kinematics, etc. Today, I am going to discuss about the flow descriptions. So the flow description, while fluid is flowing, we should able to say which type of flow and how the fluid particles are will be behaving, how the fluid particles are moving in a fluid path that we, one should recognize, and we have to compare in real fluid flow problems. So the flow pattern may be described by means of streamlines, stream tubes, path lines, streak lines. So there are basically four types of flow descriptions. This is also known as flow patterns. The first one is a streamline, then a stream tube, a path line, streak line, and also timeline also can be discussed. That is also one type of flow pattern. So first we'll discuss. We'll go through the streamline. Basically, the streamline can be defined as when a fluid particle is moving. If you assume that that particular fluid particle is moving in a curved path, then tangent of that curved line at any point, tangent to that curved line, tangent to this curved line at any point will give the direction of velocity of that fluid particle. So if the fluid particle is moving in this way, or it is moving, another fluid particle is moving like this, the tangent to this tangent to this curve at any point, you can take a tangent at this point, a tangent at this point will be giving the direction of velocity of that particular fluid particle. That's why they say imaginary curve or imaginary line drawn through a flowing fluid in such a way that the tangent to it at any point gives the direction of velocity of flow at that point. So therefore, the streamline is a imaginary line. Imaginary line, the curved for that curved line, imaginary for that imaginary curved line, the tangent at any point gives tangent to that curved line gives the direction of velocity. Also, it can be defined as a streamline flow fluid is defined as a flow in which fluids flow in parallel layers such that there is no disruption or intermixing of layers, and at a given point the velocity of each fluid particle passing by remains constant with the time. So always there will be no disruption between the fluid particles or between the fluid layers while the fluid flow is taking place. So the fluid flow is similar to laminar flow. The fluid flow the layers will be moving one over other, or adjacent layers will not interact with the flow of another adjacent layer. The fluid particles and fluid layers will move in its particular paths. They will not come into the path of others fluid particles, and they will not disrupt. So such type of flow is also known as a laminar flow. So in streamline flow also fluid particles will not disrupt each other. So here we'll understand a fluid particle about two-dimensional ordinate and for a three-dimensional ordinate. So you can locate a fluid particle while different fluid particles are moving in different curved paths like this. Okay, so here if you consider a fluid particle at this instant, at p of xy, at this instant, the horizontal velocity axis, and you can take a vertical velocity component along y direction. If the velocity v at this instant, the tangent to this curve gives the velocity, direction of velocity of that particular fluid particle, direction of velocity of that fluid particle at that instant, at the p of xy ordinate. At this instant, the velocity of fluid particle is capital V, and this can be resolved into two components, about x and about y. So about x, the velocity component is a small u. So about if this is a velocity of a fluid particle about x, the component is small u, velocity component is small u, and about y, the velocity component is small v. So, and the angle between u and capital V is theta. So this gives the direction of velocity, and you can say that there are displacements. If the displacement vector is ds, you can write u as dx. Displacement about x direction is dx. Similarly, in displacement about y direction is dy, and so the displacement of vector ds is dx and dy. So in a three axis, in a three-dimensional plane, how can you represent a fluid particle? Here also we have to imagine a curved line about which a fluid particle is moving. At a particular instant, if you draw a tangent to that curve, that gives the velocity capital V. So about as it is a three-dimensional plane, there will be three components of velocity about x, about y, and about z also. The displacements about that particular directions are dx, and about y direction is dy, about z direction is dz. So the velocity components about x direction is small u, about x direction, and about y direction is v, and about z direction is w, small w, small u, small v. These are the three velocity components of a particle while it is moving in a three-dimensional plane. So similarly, if it is moving in a two-dimensional plane, if you want to analyze a fluid particle and its velocity, acceleration about a two-dimensional plane, about a two axis, then there will be two velocity components, u and v, and the direction will be theta. Similarly, there will be displacement coordinates about x is dx and dy. So the same thing can be applied in a three-dimensional plane also by considering the z-axis also, and its respective velocity in the z direction is w, and the displacement is dz. So since a fluid is composed of fluid particles, the pattern of flow of a fluid may be represented by a series of streamlines obtained by drawing a series of curves through the flowing fluid, such that the velocity vector at any point is tangential to the curves. So series of streamlines, as a fluid is composed of so many particles, we can draw so many imaginary curved lines, and for all that curved lines at any instant, if you draw a tangent, it will be giving the particular fluid particles velocity in that direction. So the particular figure shown streamlines for a flow pattern in the xy plane, in which the streamline passing through a point p of xy is tangential to the velocity vector v at p. So here we have discussed earlier, the small u is a component of velocity about x, small v is a component of velocity along y, and see about theta, the velocity of a fluid particle v will be represented. Now, if small u and small v components of velocity, then we can write as v is the velocity vector of a fluid particle, so which is drawn about a curved line. Okay, about a curved line, if it is drawn like this, the tangential velocity v becomes like this. Then its horizontal component will be u, and vertical component will be v. So about an angle of theta. So from this, tan theta is equals to v by u. So v by u is tan theta. Otherwise, if the displacements about x direction is dx, and about y direction displacement is dy of a particular vector ds, then tan theta also can be written as dy by dx. So therefore, tan theta can be represented as small v by u is equals to tan theta is equals to dy by dx. So where dy and dx are the components of the differential displacements of a streamline in the immediate vicinity of p. So therefore, the differential equation for streamlines in the xy plane also can be written as dx by u. equals to dy by u, or u into dy minus v dx. From the same derivation, we can write this equation u dy minus v dx is equals to 0. So this is the expression of streamline for a two-dimensional plane. So it can be expressed as dx by u is equals to dy by v, or u into dy minus v into dx is equals to 0. So if it is a three-dimensional plane, we can express the streamline expression for a fluid particle is dx by u is equals to dy by v is equals to dz by w. Since a streamline is everywhere tangent to the velocity vector, there can be no component of the velocity at right angles to the streamline, and hence there can be no flow of fluid across the streamline. If the streamline flow is taking place like this, and there will be no flow across of streamline, so therefore there will be no velocity component at right angles to the streamline. Further, in steady flow, since there is no change in direction of the velocity vector at any point, the flow pattern is not changing. So there will be a steady flow and unsteady flow. The streamline categorization will be there. In a steady flow, as the velocity and characteristics of the fluid will remains constant. Therefore, there is no change in the direction of velocity. So, but in case of unsteady, these properties will vary. In unsteady flow, the direction of the velocity vector at any point will change with respect to the time. Therefore, flow pattern also changes with time to time. So at every second, the flow pattern will change. Therefore, a steady flow streamline pattern remains the same at different times. But for an unsteady flow, the streamline pattern may be changing from time to time. So this is a difference of a streamline pattern in case of steady flow and unsteady flow. So here some of the examples we can observe for a streamline. Example is one is a smoke. The smoke is an example of a streamline, and the smoke emitting from different equipment at different situations you might have seen. A smoke similar to a laminar flow will be one of the examples, similar to laminar flow. Fountains are another example of laminar flow. The water molecules move in a straight line, so they do not mix with each other. The particles will not come into the way of other particles movement. Therefore, that is similar to laminar flow. You can take the example of the streamline. Similarly, aircraft wings designed to create laminar flow. The air molecules move in straight lines and do not mix with each other. So this helps to reduce the drag and increase the lift of an aircraft. So water balloons, when filling the water into the balloons, the water molecules move in straight lines. So that is also one of the example of streamline. Next, blood flow is an example of laminar flow. So the blood cells move in straight lines, and which doesn't interact with others path. Therefore, that is also one of the example of a streamline. Then the stream tube. Then coming into the second flow pattern is a stream tube. The stream tube is nothing but composition. Otherwise, is a combination of group of number of streamlines. So that is nothing but a stream tube. So if you join the number of streamlines in a particular fashion, so this is in a circular shape, but it may not be a circular one. So it may be into a different cross section also. But the stream tube is nothing but a combination of the group of streamlines. The stream tube is this is also imagined tube, because once a streamline is imagined, the stream tube is also imagined. Group of streamline, not a real line, it's a imaginary line. So imaginary line, therefore the stream tube is forming such type of composing such type of imaginary lines. Therefore the stream tube is also imaginary. A small closed curve which may or may not be circular, may or may not be circular. So since the stream tube is bounded on all sides, the streamline, and since the velocity has no component normal to a streamline, therefore across the boundary, so you see in say inlet and outlet, there are two boundaries, and the across the stream tube there will be no component, as there is a no component of velocity, no particle is moving across a streamline. Therefore, across the stream tube also there is no cross flow. Therefore, fluid may enter or leave only at the ends. May be entering and leaving at the ends only. There will be no cross flow. So, a stream tube with a cross-sectional area small enough for the variation of velocity over it is to be negligible is sometimes termed as a stream filament. Sometimes it can be called as a stream filament, as the velocity variation is considered as negligible. Therefore, it can be called as stream filament also. The concept of stream tubes is quite useful in analyzing several fluid flow problems, since the entire flow field may be divided into a large number of stream tubes, thus yielding clear picture of the actual pattern of flow. Here the stream tube is divided into so many areas in order to analyzing the different types of different stream tubes. The one stream tube is again furtherly it can be subdivided, discretized into so many parts in order to analyze the flow field. However, only in steady flow pattern stream tube is fixed in space. So, but in unsteady, it is not fixed in space. The general continuity equation can be applied to stream tubes, though it has no solid boundaries. The continuity equation can be applied over a stream tube. In steady flow with a uniform velocity, all streamlines are straight and parallel. So, for a steady flow, it is as a streamline is straight, so then they will be identical also. So we can see the another type of stream tube, and its example in this, as there is no cross flow across a streamline, there will be no cross flow across a stream tube also. And here one of the example is the flow through pipes with a low velocity, the uniform steady flow flowing through at a constant pressure while it is flowing through a pipe, we can be taken as an example of a stream tube. Next, another flow pattern is path line. So the path line means here we will be considering only one fluid particle. A particular fluid particle will be traced throughout its journey for a period of time, for a particular period of time. How the particular fluid particle is moving in a flow field, and that all that areas, all that points should be connected, so that we'll be getting the path line. Path line means a single fluid particle as it is moving. If you take a fluid particle at this time at t naught, at t equals to 0 or at t equals to 1 at first second, if you observe the fluid particle is started ejected at this location, and now if you trace this path of a fluid particle at different seconds at t equals to 2 at this location, you have to connect it. So the fluid while a fluid flow is taking place, through which if you select a fluid particle at every second of time, if you connect it physical positions, then we will be getting a path line. A path line may be defined as a line traced by a single fluid particle as it moves over a period of time. That is known as path line. The path line will show direction of the velocity of the fluid particle at successive instants of time. As indicated earlier, a streamline, on the other hand, shows the direction of velocity of number of fluid particles at that. So at that instant, that gives the direction of velocity of number of fluid particles, or for a particular, if you select a particular fluid particle, for that it will give the velocity at particular location. A fluid particle always moves tangent to the streamline, and in the case of steady flow, since there is no change in the direction of velocity vector at any point with the time, the streamline is fixed. The streamline is fixed in space. So if in a steady flow, these two are identical. Therefore, the steady flow path lines and streamlines are identical. Because there is no change in velocity, the velocity vector is not going to change. Therefore, in steady flow, the path lines and the streamlines are identical. However, in unsteady flow, since the direction of a velocity vector at any point may change with the time, the streamline may shift in space from instant to instant. Therefore, in a unsteady flow, the path line may not be same as the streamline. In unsteady flow, every time the velocity vector direction will be changing, these two becomes unequal. In path line, follows one streamline at one instant and another at the next instant, and so on, so that the path of the particle may have no resemblance to any given instantaneous streamline. In other words, in unsteady flow, these two are different. The path line may intersect at different timings. A path line is a Lagrangian concept in that we simply follow the path of an individual fluid particle as it moves around in the flow field. So, in a Lagrangian concept, there are two concepts in fluid flow, fluid mechanics. One is Eulerian concept, another one is Lagrangian concept. In a Lagrangian concept, one single fluid particle will be identified, and its characteristics will be studied over a period of time. That is the Lagrangian concept. In case of Eulerian concept, for a particular instant, at every different instance of timings, the fluid mass will be selected at that particular region. That fluid mass will be analyzed. The example of a path line is a balloon floating in the air. So at a different instant of time, at different positions, the balloon will be positioned, will be located as it is moving in the air at different timings. If you locate all the positions of a balloon in the air at different instants of times, and that travel by a balloon will be known as the path line. For a flow which doesn't change with the time, the streamline, streak line, and path lines will be same. Another flow pattern is a streak line. A streak line, in a streak line, how do you understand this one is experimentally, if you inject a dye at different timings, at different instance of time, so that fluid, how it is moving through that another fluid. So the dye is different color, and entire fluid is different color. So that how the fluid is moving through that particular fluid, how that particular dye, colored dye will be moving. If you trace out that one, you can draw a line. So the particular line represents a streak line. So yeah, in other words, the streak line it is defined as a line that is traced by a fluid particle passing through a fixed point in a flow field. So at a different instant of times, it can be drawn for a fixed point. Okay, so in such cases, we can understand through by injecting a different color of liquid through a flow field. In steady flow, since there is no change in flow pattern, all these lines are same: streamline, streak line, path line. So now we will understand the streak line, how it can be drawn. So in this diagram, what is happening for 10 seconds of time, for 10 seconds of time, 1 2 3 till 4, for 10 seconds of time, the dye is the colored dye is injected. So at second at t equals to 2, the particular fluid second particle will be second at seconds will be at this position. At third second it will be at this position, and it will be moving. If you study about 10 seconds, that the fluid particle injected at first second will be at this location. If you connect all these points with a dotted line, that is a path of that line, the path of that fluid particle over a period of 10 seconds. Okay, so this is known as a path line. This is known as a path line of that fluid particle, because we are selecting one fluid particle and we are tracing out its location for a period of 10 seconds. At every instant of time, we are locating its position and joining. So, but at a time, at a second, at t equals to 2, if you inject a second particle, okay, and it will be traveled for a remaining 9 seconds, and this will be the path line of the second fluid particle. Similarly, path line of a third fluid particle. So these are the path lines of fluid particles at different seconds. Till 10 seconds we will be observing like this. So remaining, if you inject a fluid particle at a fourth second, remaining 6 seconds we will be following its a fluid particle path. Therefore, that is a path line. So now what is happening if one at first second we release, and at second it is at a different place, but while we are injecting a fluid particle, yet all this through all this 10 seconds we are injecting the fluid particles. But if you want to draw a straight line of fluid particle injected at a 10th second, is it will be connected to the 10th second is here. Here we are injected the color dye, and it will be connecting the 10th of all the fluid particles. The 10th second of all fluid particles will be connected. This is a fixed point. 10th of, if you injected a fluid particle at first second, it's a 10th second, at 10th second its position is here. If you inject a fluid particle at second t equals to 2, and its fluid particle location at the 10th second will be here. And if you inject a fluid particle at the third second, and its fluid particle location at the 10th second will be here. So like this, at the 10th second, if you if you connect all these 10 seconds of all the fluid particles, even though they are injected at different timings, but at the 10th second, all their positions, if you connect with a line, the particular line is known as streak line. That is nothing but connecting the fixed points, connecting fixed point. So if you want to draw a streak line for 9th second, the 9th second of all fluid particles, so where the 9th second of first particle, but even though injected at t equal to 1, t equal to 2, t equal to 3, they are injected at different timings, but at 9th second, the positions of all these fluid particles are connected with a solid line. So that particular line is known as a streak line. But path line means 1 to 10 seconds you have to follow. 1 to 10 seconds you have to follow that particular fluid particle only. And if you draw a line through all its position through which it has been traveled, then particular line, that particular connectivity is known as a path line. But irrespective of the time it was injected, if you connect all these lines at a particular timing, then you can call it as a streak line. Similarly for 8th second also, 10 seconds also, for 7th second, for any second, for whatever the time it was injected. But if I am locating the particular fluid particle at the 8th second, irrespective, it was started its travel at t equal to 1, t equal to 2, but 8th second I am joining all these fluid particles locations, then you can call it as a streak line. So here we can see very clearly the time at t equals to 1 it was injected and is flowing like this. So this is known as a path line. This is known as path line. So at t equals to 2 it was injected, but if you connect at t equal to 2, the first particle at t equals to 2 it was here. So therefore this is called as a streak line. This is called as a streak line. So at t equals to 3, it was injected and it is flowing like this. This is it's a particular path line, but it is connected. The at the third second it will be here, while it was injected at t equals to 2, at t equals to 1 it was injected, at the third second it is here. If you connect all these fixed points at t equal to 3, the particular line is known as a streak line. The streak line is different from path line. So for your study flow, streamline, streak line, path line, all will be same. In streak line, the dots represents the position of each of these particles at a time indicated. The dotted lines represents the paths of the particles are path lines. So this is all the explanations regarding the if you inject the colored dye through a flow, then at different seconds how they will be traveling, how do you identify its path line, how do you identify its streak line is. And then examples of the streak line is the line of smoke coming out of a chimney is a example of a streak line. A dye when injected into the flowing fluid and a resultant colored lines after some time gives the streak lines. Next, timeline. Timeline is generated by drawing a line through adjacent particles. So in flow, at any instant of time, through adjacent particles at any instant of time. So this you can the different particles. So adjacent particles at any instant of time. If you draw through their positions, so that will be known as timeline. The difference is between these all these lines for a for a study and unstudy flow. With respect to these two classifications, you can vary these all flow patterns. So in a study flow, streamline, path line, streak line are coincident. These will be same, identical. Okay, but here stream tube is nothing but a composition group of streamlines. In a unsteady flow, these are all unidentical. So you can see here in this table, the streamline is a imaginary line showing the positions of various fluid particles. Whereas streak line, it is a real line showing instantaneous positions of various particles. So it's a real line that we are drawing, but in case of streamline, it is a imaginary. Path line is also a real line showing the successive position of a single fluid particle. When single fluid particle is traced, that is known as path line. The particles may change streamline depending on the type of flow. Based on the type of flow, for a steady flow, they will change. For they will be same. For steady flow, they will be same. For unsteady flow, they will be different. Similarly, in streak line also may change from instant to instant. Particles may cross its path lines. But streamlines can't intersect with each other. They are always parallel. If you take a steady flow, in which the streamlines are drawn, there is no intersection between the fluid particles. A streak line changes with the time. Two streak lines may intersect each other. Two path lines for two particles may intersect each other. In a streamline, there is no flow across of it, but in streak line, flow across a streak line is possible. Similarly, in path line also, the intersection is possible. So these are the some of the differences between the streamline, streak line, path line. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.